started then. Okay. Everybody for another week. I kind of have a plan laid out for the next this week and next week. If you didn't know, next Wednesday we're going to be having our term to go over sections 3.6 and everything we've done in chapter 4. We will do in chapter 4 besides 4.6 because I'm saving that until after. This is the last midterm. There's not going to be we're going to be learning some stuff after that, but that's just going to be additional final. That's after that. So yeah. So you can feel free just for yourself to keep track of what's going on. Quiz on Wednesday. I'm actually so the quizzes from last week actually turned out really well for the most part. So really glad to see that. Hope it was a little bit better. I don't think hopefully this one shouldn't be too bad. We're going to be doing a lot of examples of U-Substitution today. I'm just going to get this idea across. I introduced it last time, but there's still some nuances that we want to discuss with it. So that's what we'll do. So again, so I'll do, we'll just do a simple kind of a more common example to start off with. So let's say that I have this integral and I want to be able to evaluate it. Well, at the moment, I can't, I can look at my general formulas that I have, right? Which are, if I have, u to the n power du, if I take a constant times a function, integrated, that constant just comes to the outside. And then, is that it? Oh, and then of course, if it's just the constant, say k. Now, I don't see anywhere where I can take what's here and directly apply it to this integral. And so at first, it may look as if we have a problem where we can't use any of these. But the idea here is I want to do substitution, right? So I take this guy that looks a bit harder and try to turn it into something easier, right? Kind of try to pull it back to where it came from, right? Like, because we know that this is the derivative of something. And so if we can figure out maybe, what piece might have came from that, then we can pull it back and do it simply, right? So on this example, right, the thing that's the biggest problem is having this x isn't too bad, but this square root part that's a problem, right? So what I'm going to do is I'm going to take the thing on the inside, which is the 1 minus x squared. I'm going to let that, I'm going to call that my u. Okay, so I'm going to put give a new variable inside here. So I'm going to let u be 1 minus x squared. Okay, so if we're changing things in terms of u, right? Because I want to replace everything with some sort of u, then I need to change this in piece as well, because I'm no longer doing things in terms of x, but I'm doing things in terms of u. So the idea here is I want to figure out what the derivative of u is, right? So what is, if u is 1 minus x squared, what's the derivative of u? Negative 2x. Okay. So it's 2x and negative with the outside of the x squared. The 1 just disappears, right? Now the reason I just write du is because just like we did with differentials, I'm going to take that dx piece and put it on the side instead. If it's easier to see, you could just write the derivative first. Du over dx is negative 2x, and then bring the dx up afterwards. But our ultimate goal is to replace it, so it's easier to have it up than it is to have it in this form. But these mean the same thing. So from here, right, I want to take what I've done, right, and see if there's anything that I can compare it to within the integral itself. And besides the -2 piece, the thing that catches my eye is that we have an x dx here, right? Do we have an x dx in our integral somewhere? Absolutely. It's right. It's that piece right there, x dx, right? So basically the whole numerator piece, right, if I multiply that dx up, is going to be my du besides this -2. So the way that I fix that is I just want to get x dx by itself. So I take both sides of this equation divided by -2, and I get du over -2 equals x times dx, which is exactly what I want. Okay. Now that I have x dx, and I know that 1 minus x squared is u, this integral is going to become, so nice rainbow above the u piece. This is going to turn into the integral of the square root of u, right? So that's just 1 minus x squared is u, so I plug that in. And then the x dx piece becomes du over -2. So I get this. Okay, so by doing my substitution, I have made this a little bit simpler, right? Because there's not two variables on top and bottom necessarily. All I'm doing with is just the square root of u piece, right? What can I do with this -2? So we can bring it out front. So keep in mind, right? Remember, I think we had this discussion last time. If I have, so in this case, du over -2 is the same thing as -1/2 times du. Correct? I can just take that number and write it as a fraction times that du piece or times x, whatever the situation is. So again, appealing to our constant rule, whereas if I'm taking an integral that I can pull the constant out, I'll do this here. So I'm going to rewrite this as -1/2, just bring the -1/2 out, integral. Okay, now in what way could I rewrite that square 1 over square root of u? That would be beneficial to me. U to the -1/2, good. Okay, and then times du, right? Okay, so there we go, there's my integral now. Okay, this is great because now I see this rule, okay, which is u to the n du is going to be u to the n plus 1 over n plus 1 plus c. So when I apply it, I'm going to get -1/2 times, and then we're going to get u to the, what's the power going to be? Yeah, so we can take -1/2 plus 1. So I'll write that out. -1/2 plus 1 over -1/2 plus 1. And then I'll put a plus c on the end. Now, let me address this because we addressed if you are doing multiple terms, but if there's a constant, right, on the outside, many of you might think first, oh, well, I need to put the plus c in here. But again, if I take a constant times another constant, it's still a constant. So I don't need, I can just save it till the end. Always just throw the plus c at the end. I have to put it where it is here just for formal reasons. But you can always just throw it at the end, right? So after further simplifying here, we're going to get -1/2 u to the 1/2 over 1/2 plus c. And then these 1/2s cancel. Or you can think about that 1/2 flipping up to the 2. So I get -u to the 1/2 plus c. Am I done? No, why not? Yeah, so exactly. We started out, our integral was this, right? We started out with this integral and it was in terms of x. So I need to end in terms of x. So what was u? Good. 1 minus x squared to the 1/2. Okay.
Or you could write that 1/2 as the square root again. It's up to you, but
Just for now, but this is our. Okay. Does that kind of make sense? We're going to do more examples and see some more cases, but that's the general idea. Okay. Good. Awesome. So let's kind of address, because you know, there's going to be situations where maybe, so the book kind of gives an example like this, and it wants you to say, you know, what is the integral of this. Now, technically, we could do this because we actually know a function whose derivative is this guy, but we want to, everything we're doing in this chapter is isolated from chapter 6, right? So in this case, I have to try to do U-Substitution rules, right? So let's talk about why this one doesn't work, but that one does, right? So in the same case, I could try to call U 1 minus x squared, right? Again, just try to like the last one, that thing inside the square root, right? So then what would my du is going to be the same thing, right? Which is going to be negative 2x dx, right? What's the problem with this one though? Yeah, but couldn't I mean, so I just have dx though. Couldn't I just do, you know, something like this maybe, you know, just get solved for the dx part by itself? Does that work? Yeah, I mean, if you take this thing and put it in, you're gonna have no matter if you get that negative 1/2 to the outside, you'll still have 1 over x times the square root of u cu, and then you have to try to figure out something with that x, and it still wouldn't help. It would give you a lot of the same. So in this case, this doesn't work, right? And the key thing why it didn't work is because we needed that x piece, right? We needed just like here where we had the x dx and we could figure it out, we couldn't do the number here, right? We can always take constants and move them around if we need to, but I can't do those variables. Okay, so if you get to a case where, oh, I want to call this u, but there's nothing to match with my du, you either need to try something else, or it's very possible that this won't evaluate. So, yeah, then we get into situations. Okay. Let's do another one. So we'll do okay, so this one will be a bit interesting. Okay, let's say I have this one. And I want to take the integral of this thing. Okay, so I have x over the square root of x minus 1 dx. Okay, so again, it doesn't fall into any of my rules, right? So I can't do anything with it at this time. But what, I don't know. So what should my u be in this case potentially? What do we think? So yeah, we're gonna let u be the thing underneath the square root, which is the x minus 1 in this case. Okay. What's du? 1 dx, right? Just like that. So du is dx. So I could replace du and dx, and it wouldn't change anything. It'd be the same thing, right? What's the problem with this one? We still have this x up here, right? Right, and the issue with this last one is there wasn't really a simple way to rewrite the u term, right? I couldn't figure out how to, how to write that extra x I had over here, put it in terms of u. right? And make this work, turn it into a U integral. Is there some way, maybe in this case, that I could write this x into U? It's U plus 1, right? So this U equals x minus 1 also tells me that x is equal to U plus 1, right? So yes, I can't take this x and use it with the du part. However, there's still a way to easily replace it, right? Which is with this U plus 1 piece here, right? So what's going to happen is this integral, so I'll go down in this case. This is going to be equal to the integral. So we have the square root of U, right, on the bottom, because we said U is x minus 1. And dx is the same thing as du, because it's just du is 1 times dx. So then what does that x on the top become? U plus 1. So we get this. Okay. Now we need to deal with this guy. Because it still isn't necessarily in one of the forms I like, but is there maybe a way I can try to simplify it? So this is the same thing as U to the so you're saying, so this is the same thing as U plus 1 times U to the negative 1/2, right? Okay, good. So again, maybe similar to over there, I can maybe pull this up, right? And so this is the same thing as U plus 1 times U to the negative 1/2. Can I take this U to the negative 1/2 and multiply it with each of these terms? Yeah. What do I get when I do that? We get that, right? Another way to see this, right, is so sometimes it's easier, we can bring it up and rewrite it and multiply it. I can also, the issue in this case was if I tried to divide, there's only one term on top, right? So there wasn't really any sort of simplification I could do. But on this guy, I can take the square root of U and divide it from both terms, right? Square root of U from U is just U to the 1/2. Square root of U from 1 is U to the negative 1/2, which is exactly what we get here, right? So you're going to have problems. I think, I can't remember if the book actually offers an example like that. There are some, at least in the problems. So again, I would encourage you strongly to do all the problems that are going to look like this, right? I might even have, let's say I might have x squared plus 3x plus 2 over, the square root of x, like this, right? If you come across a problem like this, right, the idea may not just to try to do U sub, right? We may first try to see if I can simplify it, right? Go ahead and divide everything, right? Because here I could take square root of x from each term, and then I could easily just use power rule in each one, right? Because this is the same thing as x to the, what's x squared divided by the square root of x? Good. And the reason for that is because this is the same thing as, so square root of x again is x to the 1/2. And if I'm doing, this is a little far, I guess, for some people. If I have x to the m divided by x to the n, this is the same thing as x to the m minus n. So just some rules of exponents that you should be familiar with at this point. So 2 minus 1/2 is 3/2, right? 1 minus 1/2 is just 1/2, and then plus 2x to the negative 1/2, which again is just summing at that point. So then I can take each piece. But anyway, that aside here, we come back to this problem. What is the integral of U to the 1/2 du going to be? So we get 2/3 U to the 3/2, which again, maybe I'll kind of rate that fully. We're going to get So this is u to the 1/2 plus 1 over 1/2 plus 1. Plus, how do I integrate u to the negative 1/2? What's that gonna look like? Right, we're gonna get u to the 1/2. Yeah, so it ends up, right, we end up getting 1/2 instead of negative 1/2, right? Because I add 1 to each piece. Then there's a plus c on the end. So then this is gonna turn into, like Blaine said, we have u to the 3/2, and then I get 3/2 on the bottom, right? But remember, if I'm dividing by a fraction, I multiply it by its reciprocal. So on a test or quiz, if you leave it as 3/2, it's fine on the bottom, but it's the same thing as multiplying by 2/3. And same thing over here, we're gonna get negative 1/2 plus 1 is just positive 1/2. But it gives us 2 times u to the 1/2. Oh, this should be u. Plus c. Okay, and then what's the last step? Plug back in. Yes. Yeah, plug back in whatever u is, right? For what u is in terms of x. So we want to put that thing back in. What was u in terms of x? So I'm going to get 2/3 times x minus 1, 3/2, plus 2 times x minus 1 to the 1/2 plus c. Negative. Okay. Does that make sense? There might be a few a couple problems in the homework that are like this. Most of the examples are going to be probably a bit clear, like this one, but it's always good to make sure you understand the concept with ones like these. So, okay, any questions on what's on the board at this current moment? Okay. Would you like me to do another example of one of these? Yes, please. Okay, great. Thank you. Okay, let's see if we can find one that's maybe a bit more challenging, but still pretty intuitive if you look through it. 23. Okay. Oh, actually, that's a good example to talk about because here's the thing. Math is a game about trying to make things as easy for yourself as possible. On 23, on the homework, we're given this problem, right? So what was your approach when you tried to do this problem?
I knew what I was expecting from trying to make it work with it. So I got my final answer. It's totally wrong. Was I got 2/3 square root of x times u squared.
Okay. So your approach was to say, let's let u be 1 plus the square root of x, right? And then try to figure out u from there, which this is 1 over 2x to the 1/2, or and then try to work this out. But again, we run into an issue of, well, I'm missing an x piece up here. And I could try to maybe substitute, figure things out, but it gets a little weird, right? What I say is I'm lazy, so it's just squared. Why don't I just square it? So what's 1 plus the square root of x squared gonna be? So 1, good, plus x, yeah. Let's do square root. From here, you just do the sum of each term, and so it follows with the rules.
That makes so much sense. That's a better thing.
No, it's good. So I encourage you to try to practice the U-Sub method so you can see it works, but you know, if it's something, like, we get into issues when it comes to like the fifth power or something where or even a much higher powers to that point where you just don't want to do the whole term. But if it's only squared, right? We know how to square something, so let's just take it and expand it out. But I understand. It happens. It always happens that once you learn like a new method, every time you see a problem that it looks remotely like it, you're like, I have to apply it. And then, yeah. So this is similar to what I was talking about over here, right? Make it simpler for yourself in terms of just like take everything and divide it. Because we don't really have an integral quotient rule. And we won't ever really have one, at least for this class. So we might, well, actually do disagree with that. I don't know. What is it?
So don't put that in.
I won't for now. I know some of you guys have to take Calc 2 in the fall, so which I'm teaching, by the way, if you didn't know. So I'll try to be nice. Okay. So great. So that's a really good example. We'll do one that's more has a bit more substitution going on in here. Okay. So there's quite a few that are like that. So maybe let's compare that to. Is there another? What other ones do I give?
29 is the next one.
29 is the next one after that. Yeah. Okay. So 29 is a similar story. Because I assume you try to do u equals 4b cubed minus 1, but note it's just squared. So if you look at number 29 in the book, it's 4b cubed minus 1 times, is it 2b? 12b. No, it's 12b. Right. So what's going to be the problem? What's the problem with this one? Right. If I try to let u be 4b cubed minus 1, what's the issue with it? We're missing a b, right? If I let u be 4b cubed minus 1, what's du going to be? 12b squared. There's the issue, right? We only have 12b, right? And I can't really do a fancy trick with that one like I did over there. We just run into an issue on this problem. So, but again, it's only squared. Just squared, you can multiply things and make it simpler, right? That's kind of the again, it's kind of the game here. If you can see, if you know how to do a simple operation instead of doing it the longer way, then you would just opt for that, right? It kind of comes to the same thing of when we were doing the natural log derivatives, right? You know, I did a big long example, but if I had something like this, right? There's no need to try to do a crazy chain rule in here to get it to work. I can simply just split this up, right? Which would look like this, right? And that becomes a lot easier to work with. But it's a similar story, right? So that's one of those things that kind of comes with practice the problems, see the ones I gave you, and try to see when does this work? Why wouldn't it work here? And it helps you to get a fuller understanding of what we're doing. Okay, so let's do one that actually does work for substitution. So so we'll do x cubed plus 6 squared. Okay, so here's the situation again. I'm not going to stop you from squaring that and then multiplying this out, right? Because it's not that bad, right? However, this one actually does work out quite nicely when it comes to U-Substitution, right? Now, why is that? You get 3x squared, right? It's actually perfect. It's exactly what we need in this case. But even if it was just x squared, the fact that you would let u be x cubed plus 6, and then du is 3x squared. The fact that the cube turns into the squared, it lines up. So now I can pair things and put things together, right? So again, it's 3x squared already, so I've already got exactly what I need. So then this integral turns into the integral of, so if I plug these things in, what does the integral turn into? Squared. Integral of u squared du. Got it. And what's the integral of u squared du? Yeah, I was just wanting to know the integral of u squared du. So, but yeah, it's u cubed over 3, right? Okay, and then what's my u? So we get x cubed plus 6 cubed over 3. So, let's make, so on the problems all the problems I give on the homeworks in the book, there are solutions to them, in the back of the book. And so this would be the solution in the back of the book. But let's suppose that you didn't decide to use sum, right? And that instead you just, when you multiplied, you squared this. So I would get the integral of x the 6th, and then it'd be 36 at the end. What's going to be the middle term when I square that? 12, yep. 12x times 3x squared dx. Let's say I multiply it out instead, and so that gave me, what do I get when I multiply 3x squared by x to the 6 plus 12x cubed plus 36? 3x to the 8th, good. 36 times 3 is 108. So we would get this, and then I'd integrate it. And when I do that, I'll just save some time, but it's just going to be our normal power rule, but with some bigger numbers. So we'll get 1/3 x to the 9th plus 6x to the 6th. 36x cubed plus 6. Okay, so you would find this, and then you would compare it to that and be like, oh no, did I do something wrong? No, absolutely not. Because so x cubed plus 6 cubed at the near the beginning of the semester I taught Pascal's triangle, which so does anybody remember what the constants are going to be in this case? Right, but there's 4 other constants here. 1, 2, not 2, that's for a square. 3, it's not 9, this actually is 3 again. And then we get 1. And then I take x cubed, so x to the 9, 3 times, so 6 times x to the 6th plus, again, I'm just doing this to show they're the same answer. And if you feel like they're different, as long as you know your process is good, that's all that matters. But we're going to get 6 squared, which is 36 times 36x cubed plus 1 times 6 cubed. Okay, so, and if I divide this, right, so here, so this is divided by 3. This ends up being 1/3 x to the 9th plus 6x to the 6th plus 36x cubed. I guess there's a plus here as well. Plus 6 cubed is 216.
So once I multiply it out, I actually get the section 216 here if I multiply that one, right? So now, now it looks like it's different, right? I have 216 plus C here and I have plus C here. 216 is still just constant, right? So these all kind of just get pulled together into another big constant, right? So this and this are essentially the same thing. Okay. So all that being said, if you do this, great. If you do this, great. Just figure out what's the simplest. You want to figure out what the if you can do a U-sub, then great, right? Just check to see if it works. If the U-sub doesn't work, then there's always going to be other methods that might work out. I guarantee though, if it's like a square root, like if I had this, square root of x cubed plus 6, then the only way I'd be able to do that is with a U-sub. Okay, how was that? Does that make sense? Again, the key part here is the U-sub part, right? Please keep that in mind, but also know how to do some operations. Okay. 4.5, that's basically it. There's a whole lot of examples. There's even examples that are definite as well, which the only thing you do extra is that you plug in the two numbers to subtract it, right? That's just using 4.3 knowledge on this. Okay, so any questions about this? Okay, can I move on to 4.7? So, 4.7. So the reason I'm giving 4.6 is because 4.6 talks about finding the area between two curves. Now I'm pretty familiar with the normal 165, 166 book. And in that book, they put this section with chapter 5 because the processes you learn in chapter 5 are kind of linked to the ideas presented in that section. So I'm going to save that section until after and just leave what we have for the test on Wednesday. But these last couple sections are going to kind of stand on their own. So, or last few sections. So we need to discuss those. Okay. Okay, so let's say I'm going to give you this integral. Okay, so 1 over x squared, and I'm going to go from, let's say I start at 1. 1's a nice number to start at. Okay, and I go to infinity. Okay, so infinity is not really a nice number to plug in, right? I can't, just put, infinity in here, and then that's the function value, right? Infinity is something we more study a limit of, right? So whenever you see an integral like this, we call these, and this is the section name, improper okay. The reason that they're improper is because I can't, the numbers that I have, even on the bounds, I can't simply just plug into the function, right? So let me give you another example, real quick, of another improper integral. Let's say I'm going from 0 to 1 of 1 over the square root of x dx. What's the problem with this one? Yeah, so if I put 0 in here, it's going to break, right? So the function value at 0 doesn't exist, right? So that's one type. This is another type. Let's do, and I'll give you one more, which we'll cover in a little more detail a bit. So I'm gonna take the same integrand, and now we're going to be given this, which actually I should probably no. x to the okay. What's the problem with that one? It looks like I can put both the numbers in there. Not necessarily. -2 to the 2/3 exists. It's not necessarily a nice number. Might be easier. Maybe I could put, we won't do this one, but I could put -8 there. That would actually give us a nice number, but it's not because it's going to be imaginary. The reason why I changed the last one is because it would be imaginary in that section. No, so remember our definition of integrals. Remember where these things came from, right? And that's the sum, our sum definition, right? So I'm summing up rectangles over this entire interval, which the interval is from -8 to 1 in this case, right? So I have to include every number in between -8 and 1, right? What number would be bad inside here? 0. 0 is between -8 and 1. That's a problem, right? You could evaluate this and then plug in these two numbers and get something, but it would actually be nonsense. And it's purely because 0 is in here somewhere and that breaks it down. Okay, so these three are examples of improper integrals, right? So what our goal is to be able to take these and evaluate them. Okay, and I'll do one example of each case. And we'll go from there. Okay, so, and maybe I'll use the yeah, okay, so example number. So we're gonna do the integral from 0 to infinity. 2 over x plus 1 cubed dx. Okay, why is this one improper? Because it has infinity, right? So I don't want to, whenever I evaluate the sum, I don't want to just say, I can't really plug infinity in nicely, right? So here's the idea. The steps I'm going to take to evaluate this is, instead of putting infinity there, I'm going to rewrite this. Go equals further away. And go from 0 to some other variable. Generally the I think they use B. So maybe I'll match with them, but you could use T or something. I'm gonna write the same integral now. But now what we're gonna do is I'm gonna write add this on the front, right? Because the limit as b approaches infinity of this integral is gonna give us exactly what we want, right? So, right, in this case, what I'm saying is as I have some, for my curve, I have some so I start at 0 and then I have some arbitrary b, right? That I'm stopping at, right? So now we're interested to see the curve keeps on going, right? So now I'm interested to see what happens if I let b go all the way down, right? But it works if I just use some random variable to evaluate it first and then do the rest. Okay, so let's work this out. Okay, how do I evaluate this integral? Thoughts? We're going to use U-Substitution. Okay. So what is U going to be in this case? X plus 1. Okay. And what's du going to be in this case? 1. Yeah, so it's 1 because that's the derivative of x plus 1 times dx. Okay, great. So again, du and dx are the exact same thing. Okay, so I can just replace dx with du and we're all good. And then x plus 1 becomes u. Okay, so I'm gonna leave off because our bounds are in terms of something different. I might come back to that at the end, but I have all this, some stuff going on over here, and then we're gonna have 2 over u cubed du, right? The reason I write that again is because we're doing things in terms of u, but our bounds are in terms of x. So I don't want to confuse myself and accidentally plug in the x bounds into u, right? So how do I work out? So let's look at that separately maybe for now. How do I integrate 2 over u cubed du?
To -3.
Yeah, good. So this is going to be the same thing as the integral 2u to the -3rd power du. Okay. Now let's use our rules. So what's this going to turn into? U to the -2 over -2. So whatever I put in the power, I put in the denominator. Yes.
Those 3 dashes.
So this is, just keep in mind that we're still bringing the limit and all the, like, the bounds are going with us. But the reason I didn't write it on here is so we wouldn't be confused, because we're integrating with respect to u, right? These bounds are in terms of what? X. So I didn't want to put 0 to b on here because this is in terms of u. It's a different variable, right? So keep in mind, I might even put little things here. Keep in mind that there's going to be numbers, things happening on here. I can even keep, if you want me to put the limit back here. But I'm not going to worry about putting the bounds back until I replace it back with x. Okay, so then this becomes, so we have 2 times u to the -2nd over -2, right? What does that turn into? How can I simplify that? Yeah, -u to the -2nd or -1 over u squared. Good. So that's going to be our integral here, right? Now this is so that we get the limit as b approaches infinity of -1 over u squared, and then we have a couple bounds for going from. What is u?
X plus 1.
X plus 1. So I'm going to get the limit as b approaches infinity of -1 over x plus 1 squared from 0 to b. Now I'm going to put them back because now I'm back in terms of x, so everything's same. Okay, but for now, I didn't really have it. So, or I didn't want to confuse myself by writing it down if I was replacing it back with x. So now we're back in this step. Okay, good. Now what do I do at this point? Right. So let's ignore the limit for now. What do I do with that b and that 0? Plug it in, right? So can I erase this over here? Is that okay? Do I need to leave that for anybody? Is anybody still ready? So then this is going to become the limit as b approaches infinity, and then we're going to have, I'm going to put b in here. So I get -1 over b plus 1 squared minus, and then put 0 in, I get -1 over 0 plus 1. Right. Okay. Which gives me the limit as b approaches infinity of, I can't do anything with this term, -1 over b plus 1 squared. What's going to happen with this piece? I have -1 over 0 plus 1 squared. So this in here is just -1, right? Because I have -1 over 1 squared, which is just -1. But then there's a minus, so I have minus minus 1, so I get +1. Okay. So we've evaluated the integral, so now it's just time for us to take the limit. So I want to take the limit as b approaches infinity of -1 over b plus 1 squared plus 1. Or, yeah, the plus 1. Which in reality, right, I can take the limit of each piece, and the limit of that 1 is just going to be 1. What's the limit as b approaches infinity of 1? Not 0. It's just 1, right? It's itself, right? So I'm going to take this, that plus 1 out. What do we think about that guy? Right. Then, yeah, so it's going to go to 0, right? This minus really, if we ignore the minus for now, as b gets bigger, I'm going to get like 10 million plus 1 squared. 1 divided by that. So it's going to keep getting very small, much smaller and smaller and smaller. So this piece here goes to 0, right? So even with that negative on it, still is just going to be 0. So then I get 0 plus 1. That's simply just b. So the integral from 0 to infinity of that of 2 over x plus 1 cubed dx is simply just the value of 1. What is it? Yeah, I know. I'm sorry. It's a little disappointing, but that's typically how these sorts of problems are going to work, right? And most of the book example problems are going to be ones like where you're going towards infinity, as I've seen. They're going to give cases where, so maybe I'll write one out for us. We don't have to necessarily evaluate it. But you might be given, so number 15, for example, in the book, it says that y, we want to find the area. So it says y equals 1 over x plus 1 and 3x. And it says to find the area bounded by, so it's this curve, the coordinate axes, and we want, and then the area in the first quadrant. Okay, so you might be presented with something like this, right? Where it won't just give you the integral first. You might say this, and it says find the area bounded by these things, right? So, right, if you want to just like get some points to get a rough sketch of where that's going to be, that's completely fine. It's you don't even have to. Let's see. So if I put 0 in there, I just get 1. Put 1 in there. 2 to the 3 halves. I don't know. It'll be about here. If you keep testing points, the graph is going to look something like this. Okay, so you don't need to do your crazy screw curve sketching here. If you want to be extra fancy, you can. But we just want to see kind of what the general curve is going to look like. At least in this section. There's also a section over here, but notice that we're only concerned about the first quadrant. Okay. So when it says the coordinate axis, what does that refer to? Yeah, so that means that the graph is bounded. We want the area to be bounded by the x-axis and by the y-axis. So here's x, right, and here's y. So that means that it can't pass here. It has to stay within that region. Okay. And again, the x and y-axis are here, of course, as well. But it says specifically also in the first quadrant. So it has to stay, it's bounded by these and it's bounded by the curve and it's within the first quadrant. So that means that we need to be in this area. Right? So I just want this section of the graph. So if I want to find the area, the curve again is the thing I put in, right? So I'm gonna have the integral from, so what's my left number gonna be in this case? 0. What's my right number going to be? And quote unquote, it's infinity, right? Because that it kind of gets closer and closer, but it doesn't ever touch there, right? So we get 0 to infinity of the curve. And then from there, we would follow simple processes. That one actually would be the exact same thing, except your powers are slightly larger for different fractions. You take the limit. Okay. Questions there, comments, concerns? Just, at least get a general idea of the graph and know what we're boxing between. This is kind of similar to the 4 point on 4.3 where it would say find the area underneath the curve between x equals 1 and x equals 5, right? So if I have an x squared, right, between those two values, I would go to the x equals 1 line, x equals 5 line, and then I would do the area between those two. But here we go a little farther, right? So something to keep in mind. Okay. Let's do another one. Maybe we'll actually do that exact one number up there, which is the integral from 0 to 1 of 1 over the square root of x dx. Okay, so if it's infinity, right, you're just in that case, so this is improper again, just due to I can't put 0 in there, right? So again, with the improper thing I need to do, I'm going to rewrite this using a limit, right? So I'm going to have the limit as, and we'll do b, right? And then we're going to integral from b to 1 square root of x dx. What is b going to approach in this case? So it approaches 0. From the right side. Okay, so we talked about this a little bit. It won't really affect like whenever you're plugging in, it should be the same thing as if you were at 0, right? But if I'm taking, so this graph, it looks something like, so at 1, I'm at 1, 2, at 4, at, right? It's gonna look something like this, right? Let's keep in mind that what happens if I plug a number less than 0 inside that function? It's imaginary. It's not real for purposes we don't consider this, right? That's a problem, right? If I just said goes to 0, that's a problem because I can't do that function if it goes to 0, right? Because it's because one side doesn't exist and the other side does, right? Instead, we just want to consider the area that we're working with, which is here in this case. So I'm going to have 1 on the right side, and then I'm only approaching 0 on the left side, right? I'm not actually at 0. I don't have anything before 0. Everything is on the right at 0, right? So that's why I need to specify 0 to the right. Now, again, when we plug in, it won't affect anything, but just something to keep in mind while we're when we're doing this, right? There's a little bit of a nuance that we need to worry about, right? Okay. How do I evaluate this integral now?
Substitute for X.
Okay, so let's play around with that idea a little bit. If I let U be X, well, but I mean, you don't need another X, right? What's the derivative of X?
1.
1. Right? So what happens is that this turns into the integral from whatever bound to 1 over the square root of U du. Did you make your integral any easier? No, right? It's the same integral, right? So we don't need to do U sub here, right? Because it's just X. It's just X, right? Let's just take this and rewrite it. So b to 1 of x to the what power? A to 1 half. Good. So what is the integral of x to the 1 negative 1 half? I think I heard it overall. So x to the 1 half over 1 half. That's great though. I love that many people are talking that occurs. Okay. And then we want to evaluate this from b to 1. Okay. Again, if I want to write around the side here, x to the 1 half over 1 half is the same thing as 2 times x to the 1 half. Just multiply that reciprocal. And so what that leaves me with is I'm going to have, so I'll write this, I'm going to put parentheses down here, 2x to the 1 half. So I'm going to get 2 times 1 to the 1 half minus 2 times b to the 1 half. And we have the limit as b approaches 0 from the right side. Okay, so so what's my final answer going to turn into at this point, right? I have, what's 1 to the 1 half? 1. So 2 times 1 is 2. If I let the limit as b approaches 0 from the right of 2 times b to the 1 half, what's that going to be? B. What is it? It's 0, right? Good. Just turns into 0. So I have 2 minus 0. Again, underwhelming, I know, sorry.
Why does it turn into 0?
Well, so I'm taking the limit as b approaches 0 from the right of 2 times b to the 1 half, right? Remember when we were doing limits, right? If I could just plug into the function, then just plug into the function, right? It was only when we couldn't plug in where we had to do weird things, right? Or do some sort of procedure, but I can just put 0 into b. So then it becomes 0. So we get 2 minus 0, which is 2. Okay. So even in these circumstances where I have an area that doesn't seem like it will come out to anything, it can exist actually if it would be 2 in this case. Now, this may bring up discussion though of, does this always happen? Can I, if I decide to make the bound anything I want to, can I always find something? So let's say we have, I'll just take 1 over the square root of x again. I'm going to go from 1 to infinity. Right? So again, so we already know what the integral of this is, and I can change. Let's change this to the limit, right? It would be approaches to infinity of 1 to b, 1 over the square root of x dx. Infinity of 2 x to the 1 half from 1 to b, which is the limit as b approaches infinity of 2b to the 1 half minus 2 times 1 to the 1 half. Okay, so again, you just evaluate the integral, and I plugged in b and 1. What's the issue with this? Well, this does turn into -2. That's not the issue though. That's fine. That's not the issue. Right? What if I take the limit as b approaches infinity of 2 times b to the 1 half, that's infinity. Right? That's that doesn't give me an area, that just blows up, right? So what that means, the reason why that happens, in this case, even though it seems like it does go to 0, is that it goes down so slowly that you can't actually say anything about it. So it just keeps building. It doesn't ever stop building it. It just keeps going, right? So this, yeah, so like we said, you get infinity -2, which is nothing. So in this case, this is just a bad problem. And I think they use this terminology. Let me see. Ordinary. Maybe it'll come up. There's usually a words oh no, okay, there it is. I was like, I think it's in here somewhere. So in this case, we say, so in this example, since we got it to be a number, this improper integral is called convergent. Which meant that it converged to something nice, which it gave us a number out of it. But this example, it's a divergent integral, which means it doesn't converge to anything. Which means that it doesn't work out the way you would want it to. So we can't get a value out. Okay. So there are examples where it won't work. I think the book just has you do, it just says to find the area. It does have, I don't know if I might have gave that one. It's number 27, but keep in mind, I can't remember if I said this already, but I'm moving a little bit ahead of my notes just to try to give more time at the end. So on this day was supposed to be 4.5, and then that was it. But I went ahead and moved ahead to 4.7. So you want to go ahead and look on the next day. So what we get. But yeah, anyway. Questions here? Yes.
Rewrite that as the limit of b approaches 0, x to the half over half. How do you rewrite it as it is right underneath it?
How do I rewrite it here?
Yeah.
Well, remember, I kind of wrote this on the side. If x to the 1/2 over 1/2 is the same thing as 2 times x to the 1/2, because I take the reciprocal of 1/2 and multiply it. So that's where I get 2 times x to the 1/2 in that case. So that's just easier to plug into. If you don't change it to I don't take off points, but in these situations, it will make it a little harder. So I would like it a little weirder to figure out. So I would encourage you to do that. About 5 minutes. Maybe we can do a final example, and then we'll maybe at least introduce the next topic. Okay. So the last one, I'll just take from the book. We're going from -1 to dx over x minus 1 squared. Okay. Why is this one a problem? What is it?
Negative denominator.
One's inside the interval, and so I can't have that. Okay, so the way that I do that is I do an integral like this. Is I say, okay, 1 is my special point, so I'm going to kind of work around it. What I mean by that, right, is if I so I'll take an example here again. This may have been like a theorem or something that we already used, but if I'm going from A to B under an area, right, of a curve, and then I take some point C in the middle, the integral from A to B of my function, same thing as the area from A to C plus the area from C to B. Do we see that? Does that make sense? I'm just splitting it up into pieces. right? So I take one area and add it to another area, but it's the same, it's still the same thing, right? So I'm gonna do that here, and I'm gonna rewrite this as the integral from -1 to 1 of dx over x minus 1 squared plus the integral from 1 to 2 of dx over x minus 1 squared. Okay, so that 1 is a troublesome piece, so I'm gonna kind of move it around a little bit. Okay. Now, of course, again, 1's still a problem, so my limit's gonna have to come in. And we're gonna have 2 pieces, right? So maybe we'll look at each part and then just add together at the end, right? So we'll call this guy 1 and we'll call this guy 2. So 1 is the same thing as I'm gonna take the limit and might need to use another letter since it's still confusing over here. We'll do b approaches 1. -1 to b of dx over x squared. Okay. Now, someone tell me, is that just gonna be 1 in general? Or should I say one side or the other? What do we think? 1. Okay, 1 in general. So 1 in general would work. And I think when we evaluate it. But since, right, so this graph looks something like, no, it looks something like this, right? So for one piece, I'm considering only this section, and for the other piece, I'm considering only, well, actually, sorry, well, this should be, I'm considering from this section to this section, and for the other piece, I'm considering from this section to here, right? I still want to avoid trying to put just 1 indirectly or include it, or because I don't want to have this side involved. I only want to isolate this side as it is. So I'm actually going to do for this guy, it's going to be 1 from the left side, right? Because I'm on the left side of 1 in that case. 2 would be a similar story, except it's going to go. I'm going to do 1 from the right in that case, and then B 2. So now we just need to work on evaluating this, right? So maybe we'll kind of do an aside again, and this is going to work for both. Let's figure out what the integral of dx over x minus 1 squared is going to be. How do I do that? Square. Okay, so you're saying turn this into dx over x squared minus 2x plus 1. Okay, now what?
U-Substitute instead of.
Yeah, let's not square in this case, purely because the denominator makes things work. If it was in the numerator, we wouldn't have a problem. But yeah, let's try u sub. So if u is x minus 1, what is du going to be? 1 du. Yeah. So then this is going to become the integral of du over u squared, which is the same thing as, how could I rewrite that u squared? U to the negative second term. Yep. And then what's the integral of u to the negative second power?
Negative first.
And then it would be plus c in this little example down here. So I'm gonna have negative. So we have negative u to the negative first power, right? And then what was my u? Yes. So I'm gonna have negative, and then I'm gonna go ahead, since that's -1, I'm gonna bring it down. So I get -1 over x minus 1. And then it's plus c in this case. Okay, so again, maybe another example of a U-sub problem within this one, but that is how we would, that would be our evaluation there. That's both of these integrals, aside from the bound being changed. So I'll just apply them up here. So I have the limit as b approaches 1 from the left side, and then we have -1 over x minus 1, evaluated from -1 to b. And then this one's going to be the limit as b approaches 1 from the right of -1 over x minus 1 from b to 2. Okay. Good. So we're going to get the limit as b approaches 1 from the right side of, I put b in, I get -1 over b minus 1. Okay, I was curious on the thing. What is that here? Okay, so I get -1 over b minus 1. What do we get when I put -1 in there? So -1 inside this, -1 over x minus 1 there. Yeah, negative. So it'd be positive 1/2, right? And then minus that. Okay. Now what we're gonna see, even if I do this side, it's gonna work similarly. So I would just get limit as b approaches 1 from the right side of -1 over 2 minus 1, which is -1, minus -1 over b minus 1. So I'll put a line in between them. What's the problem? If I try to put one, if I try to put either of those right or left sides inside. Well, you divide by 0 and there's not, I mean, there's not really any way I can simplify that. If you want to look at the graph, that would, I mean, the one I drew, actually the graph of -1 over b minus 1 would look something like this. Right. The fact is that on the left and the right side, it still goes to infinity. And so neither of these, both of these diverge. Well, I think I put this over to the right for people in life. I'm sorry for you guys, but hopefully you got the idea from one of them. You can see that one. That this is going to diverge so that I won't get a value out of it. And then I won't get a value out of this guy either. Which even if I only get one, don't get a value out of one side, that's all that matters. So then this diverges. In other words, it doesn't exist. Okay. But there are going to be some happy situations, right, where I could evaluate it and I would get a value out. So it's worthy to pick and do this. Okay. Good. Do you have any other questions here? Three. I know some people are going to be taking next time we'll start on 4.8, which is just taking. So we're going to be in situations where we're not doing a definite integral, but we're doing an indefinite one. But there's, but we want to have a definite function, right? So we don't want to have plus c. It's not going to be like, here's my conditions. It needs to be this c, and we'll be able to figure it out. Let's bring the wood.